All right, this is a video on the relationship between exponents and logarithms. So at this point, hopefully you've been able to complete the investigation. In the investigation, we graphed a exponential function, 2 to the exponent x, and its inverse function. In this case, the inverse function has a specific name, and it's a logarithmic function. So in this video, we're going to look at how exponents and logarithms are related. As you can see from the graph, they're related inversely, which means the input of one function is in fact the output of the other function. So as you can see here by the relationship, in our exponential function we have a base b, an exponent y, and it's equal to x, the output. In a logarithmic relationship, that output of our exponent is actually the input into our logarithmic function. And I'll show you what that means in a second. The way a logarithm is constructed is we have a logarithm of a value x to a base b is equal to y. The relationship here between exponents and logarithms might be easier seen through an example. So for example, we have, say, 4 to the exponent 2 equals 16. Yes, I'm writing that over whiteout. My first video was interrupted, so I started over and whited it out. So back to our example here. An exponent, 4 to the exponent 2 equals 16. How is that rewritten as a logarithm? Well, in a logarithm, the base b stays the same. Our base of our exponent is actually the base of our logarithm. So this is written as a log base 4. And in this case, it's the log of not 2, but 16. 16, the output of our exponent, is the input to our logarithm. The output of our logarithm is actually the exponent from our power, 2. So in our exponential relationship, we have 4 to the exponent 2 equals 16. The way a logarithm works is it says the log of 16 base 4 is 2. What this really means is what exponent is 4 raised to give us 16? And the answer is 2. So using this relationship, we can convert between logs and exponents. Sometimes it's more advantageous to have an exponent, sometimes it's more advantageous to have a logarithm. So let's try a couple. We have first 2 to the exponent 3 equals 8. Let me turn off these zoom and timer stuff. You don't need to see that. Okay, 2 to the exponent 3 equals 8. So as a logarithm, we would keep the base the same. It would be log of 8 this time. Our input to our logarithm is the output of our power, or sorry, our exponential relationship. And the base of our exponent becomes the base of our logarithm. The answer to our logarithm is the exponent. So this is read as the log of 8 base 2 is 3, or to what exponent do we have to raise 2 to get 8? And the answer is 3. Now would be a good opportunity to pause the video and see if you can try B, and then in a general sense C. So I'll give you a second to hit pause. Okay, hopefully you paused it. If you didn't have an opportunity to try it on your own. But we'll run through these last two examples. So for our next exponential relationship, we have 5 to the exponent 2 equals 25. The base of the power is 5, so that becomes the base of our logarithm, log base 5. The exponent is 2, so our answer is 2, and the input is 25. And this works because 5 to the exponent 2 is 25. Or as a logarithm would state, to what exponent do we have to raise 5 to give us 25? And it's 2. For our general expression, we can use letters to represent a general expression instead of numbers. So here we go. The base of the exponent is r, so the base of our log would be r. The answer is t, so that's our input to our logarithm, and the exponent is s, and the answer to a logarithm is always an exponent. So here we have log of t base r is s, because r to the exponent s is t. Okay, so hopefully that helps you convert exponents to logarithms. going the other way, converting a logarithm to an exponent, is done fairly similarly. The base stays the same, so 2 is the base of the logarithm, 2 becomes the base of our power. The answer to a logarithm is the exponent 4, and that's equivalent to 16. The input to our logarithm is the output of our exponential relationship. Now, if you want to take a second to pause the video again, you can try B and C. Okay, hopefully you've had an opportunity to try B and C. So let's run through the answers to B and C. The base of our logarithm is 7, because it's the base of our logarithm is 7, so it's the base of our power. The exponent of our power is 2, because that was the answer to our logarithm. And the answer to our power, or exponential relationship, is 49. So here we have 7 to the exponent 2 is 49. And in this case, we have the log of 47, base 7 is 2, because 7 to the exponent 2 is 49. So hopefully we're getting a sense of the relationship here. Our general expression, let's take x, y, and z. The base of our log is x. The exponent would be our answer z. And the input to our logarithm is the output of our exponential, so it is y. So x to the exponent z is y. Now, you have a log button on your calculator, and that log button is actually the common logarithm. There are many different logarithms with many different bases. Sorry, I'm just going to adjust the screen here. But the one on your calculator is actually base 10. Now, some of you have calculators with different bases, or ones in which you can set the base, but regular calculators that don't have that just have a single logarithm button, and that's this one. And that's log base 10, and you can actually see maybe the second function log is 10 to the exponent x. So that shows you that 10 to the exponent x, it's a power with a base of 10. The logarithm also has the base of 10. So how is this useful? Well, that button will help you evaluate any logarithm with a base 10. So logarithms to the base 10 are called the common logarithm. When writing the common logarithm, it's common to omit the base. So we don't need to write log of 100 base 10. We can simply write it as log 100, and the base is assumed. So base 10 is assumed, unless otherwise stated. So in all the examples we already wrote as logarithms, the base was not 10, and it was stated as something else, in this case 4 or 5 or 2 or 7 or x, but it is 10 unless you state otherwise. So how could we evaluate these? Well, we could just plug them into our calculator, and if we do the first one, that would be the log of, how many zeros are there? 1, 2, 3, 4, 5, 6, so that's log of 1,000,000. So if we hit log 1, 2, 3, 4, 5, 6 of 1,000,000, we get 6. Why do we get 6? Well, the reason we get 6 is because as a logarithm works, we're looking for the exponent that we would need to raise 10 to get 1,000,000. And in this case, the exponent we would need to raise 10 to is 6, because 10 to the exponent 6 is a 1 with 6 zeros. We can turn this into a power to see that, and that might help us come up with the answer without using a calculator. So if we were to, say, rewrite this as a power, we would need to say that this equals x. X will become our exponent, so 10 to the exponent x is 1,000,000. 1 with 6 zeros. And to find our answer, if we change the base of our power, so instead of 1,000,000 to the exponent 1, we could rewrite that as 10 to the exponent 6. And now when you have a common base, you can equate the exponent, so x would equal 6. You can do similar for B and C. So I'll do B. If we set this equal to x and rewrite it as a power, the base of the log is 10, so it's 10 to the exponent x equals 0.123441. And we need to ask ourselves, to what exponent do we have to raise 10 to get, not a tenth, not a hundredth, not a thousandth, a 10,000ths, 100,000th. And it would be, well, if we move the decimal 1, 2, 3, 4, 5 times, we would get 1. So it would be 10 to the exponent -5 because we're moving to the right. So 10 to the exponent x equals 10 to the -5. We can equate the exponents and get -5. Timo, I'm going to give you a shout out here. That was you and Miss Pereira just knocking at the door. I don't know if you heard it or not, but you almost interrupted my video right at the end. And I don't have a pause button, so I couldn't even pause it. So thanks for that. One example left. It would be log 1. So how could we solve log 1? Well, if we set it equal to x and rewrite it as a power, we'd have 10 to the exponent x equals 1. And that would ask us, to what exponent do we have to raise 10 to get 1? And if you remember your exponent rules, that would be 10 to the exponent 0 equals 1. So that means that x is 0. And again, all of these could be done on your calculator. So let's check our answer to B. That would be log 0.1, 2, 3, 4, and 1. And we get -5, so we've done that one correctly. And log 1. So log 1 equals 0. Perfect. So that's the relationship between exponents and logarithms. And that is how we can evaluate using the common logarithm with a calculator or without a calculator.